supersymmetric quantum to supersymmetric quantum mechanics. And what the basic setup is, and what are partner Hamiltonians, how to formulate it in terms of Grassmann variables, and what are the consequences for the states and for the amplitudes in particular. I hope we'll also touch on the question of hierarchy of Hamiltonians, which coupled with the what is called shape invariance of the potential leads to almost all, if not all, of the solvable one-dimensional quantum mechanics problems. All right, so we'll work in 1D quantum mechanics, and I'm not going to touch on the higher dimensional analogs of all of this, but I believe they do exist. So the notation H would stand for Hamiltonian, and for functions for functions that are for eigenfunctions of the Hamiltonian, I will try to always use the letter phi and reserve the letter psi for the Grassmann variables. So these would be functions, and this should be a Grassmann variable. Fine. So the main idea is if we have a one-dimensional quantum mechanics problem in this form, I of course I've normalized everything to have proper units and not to have all those H bars and masses and stuff. So let us view v of x as normalized up to a constant, so that the ground state of this Hamiltonian, this quantum mechanic problem, has zero energy. So phi naught is the ground state, and its energy is zero. We can always shift the energy. All right. So interesting remark is that phi naught actually contains quite a lot of information. For example, if it's the ground state, then it has no nodes or no zeros, in other terms, and that allows us to reconstruct the potential. It is easy to see that v of x is nothing but phi naught double prime over phi naught, which is defined everywhere phi naught is defined. So that is neat. So the ground state actually has, well, practically all the information about our problem. Now, this particular form with the shifted energy that allows for a zero eigenvalue of the ground state allows us to envision a world where we can what is called factor the Hamiltonian in a particular way. Yeah, so let's see that we can actually always do it like this, and I'll explain why the W has a prime here. It's for convenience later on, but let's just now think of W prime as a sum function. Well, if we compute this the product of these brackets, if we just expand it, we'll have dx, we have the usual Laplace operator, then we have the W prime squared term. And we also have this part, which is W prime dx minus dx W prime. And of course, as it is an operator, this is just dx acting on double prime plus double prime dx, and the W prime dx cancels, and we have just this. Minus W double prime. So this is our H. And yeah, so when can we do it? Well, let's see. The only condition is for W prime squared minus W double prime. It should be equal to V of x. But V of x is a known function. It's a potential that we had in the beginning. So viewed as a differential equation on W prime, this is just a Riccati equation. And we consider, well, it can be linearized, and we, after we write it in this form, we can say that, well, we can solve it. W prime can be found from this Riccati equation in principle and many times in practice. But we're not gonna solve it here. There's no need for it, nor for any particular v's, because we'll notice much more. The W actually has a lot more meaning than that, than just a solution to some Riccati equation. Yeah, so we can. It is easy to see that if we let us introduce the proper notation. So everyone is familiar with the quantum oscillator, and these seem a lot like creation and annihilation operators. So that's how we'll call them. In oscillator language, they're usually called A and A dagger, but this is a more general case where W prime is not just X, which it is for the oscillator. So we'll use a more general letter, capital A. So yeah, so this is a nice result. We have H as it can be always factorized in this way, and similar to the problem of the quantum oscillator, we notice that if we solve this, if we find a state that is annihilated by the annihilation operator, then it automatically is the ground state of the Hamiltonian. Great, but that's exactly what we needed. The ground state had the lowest energy, and so this phi naught, it's what we need. But if we rewrite it in this, in terms of, if we expand a capital A, that would be phi naught prime plus W prime phi naught equal to 0. But that allows us to construct this expression. The W prime is actually minus phi naught prime over phi naught, or minus the logarithmic derivative of phi naught. So as the original potential V was phi naught double prime over phi naught, so is the what is called the super potential W prime is actually well, with a minus phi naught prime over phi naught. It's a very nice structure, and of course this solves the Riccati equation this phi naught prime over phi naught, so everything is good. Yeah. So let's see. Well, this is why do we consider this problem instead of the previous one? Because it's a simpler problem. It's a first order differential equation and it can be easily solved. And here we can see why the notation of W prime is used. Because we're to find phi naught, we're going to integrate it. So integrating this equation, we get that phi naught is some constant times the exponential of minus W. So of x. Well, very nice. That means if we know W, we know the ground state. And we can see what are the conditions for the ground state to exist at all. Because, well, not every problem has a ground state. And the condition is quite simple. The condition for the ground state to exist, so phi naught exists, it is definitely enough. The sufficient condition is for W to have a proper asymptotic behavior. In particular, we want W to tend to plus infinity as x goes to minus infinity, and vice versa. Oh no, in the same actually. Yeah, we have as x tends to plus infinity, we want W to have the same behavior. That means W in general. Oops, sorry. For the ground state to exist, W should look like some function of with these asymptotics. So it's W and x. All right. Fine. Well, let's see what else do we get as a bonus after rewriting the Hamiltonian in this factorized way. Well, the main idea of all of this supersymmetric quantum mechanics and the solvable Hamiltonians of the hierarchy that are produced from it, it all stems from one idea of defining a new Hamiltonian, which is called a partner Hamiltonian. Now, let us, yeah, so we call our old H is now H1, and the new partner Hamiltonian is H, we denote it as H2. And it is defined in a very simple way. It is defined as the creation and annihilation operator applied in the other order. Great. So let's see what's the structure of this problem. What's the difference and what's similar between H1 and H2? Well, if we expand we just expand the brackets, we know that A is dx plus W prime and A dagger is minus dx plus W prime. And the computation that we did here shows that the only difference is the sign right here. This particular sign well, this sign and this sign, they are opposite if we exchange the order, and that means that w prime dx still cancels, but w double prime appears with the other sign. I think that is clear, and we don't need to do the computation again. So the result is very similar. And here, instead of the minus that we had here, we have a plus. Plus w double prime. All right, so what's interesting about this partner Hamiltonian? Well, let's see. Let's use a now. Let's look at our function phi naught again. So as we know, phi naught solves h1 phi naught equal to 0, which is a dagger a phi naught equal to 0. But let's view it as if we had we have a new function. Oh, wait 1 second. No, this is fine. Yeah. Yeah. Consider not the ground state, but some other state. No, I don't know, number n, for example. And this state has energy En, which is greater than 0. So this can be rewritten as a dagger a by n. And this allows us to do this neat trick. Apply a from the left, apply to this equation, to both of the sides, and then we get on the one hand we have a dagger a by n. On the other hand, we have En, which is a constant, a by n, which is no longer 0 because n is not 0. But we notice that this is nothing else but h2. So we have the following relation, that a phi n is an eigenstate of h2 with the same energy, En, that was the energy of phi n as an eigenstate of h1. So yeah, this is neat. Well, clearly we have a symmetric relation here. If we consider, well, let's introduce again some notation. Since this phi n was a eigenstate of h1, we should put a 1 here. Yeah, and now we have a similar situation. If we have an eigenstate of h2, here we should put 1 and 1, with energy En2 by n2. Then we can write it as a dagger by n2. And applying an a dagger from the left, we arrive at the similar situation. A dagger, a dagger by n2 is, on the one hand, En to a dagger by n2, and on the other hand, it's H1, A dagger, Bn2. Great. So we have if we could in some way combine H1 and H2 in one structure, then we would have a very neat level structure of eigenstates and their degeneracy. In fact, we'll have a single state that is annihilated by A, and that would be the ground state, and it would not be degenerate. And then, of course, if this condition for W is satisfied, that is, its asymptotic behavior. And then we also would have the levels corresponding to these phi n's, 1 and 2, for n greater than 0. And they would have a degeneracy of order 2, as we see here. If we have phi n, say 2, and it has energy En2, then we can construct another function with the same eigenvalue, with the same energy, but for the partner Hamiltonian. And so this idea to unify these two Hamiltonians in one structure can be easily solved in supersymmetric terms. So the idea is the following. Let us modify A and A dagger in the following way. Let us introduce new operators. Now here I am not sure of the usual notation, which of the following well, I guess Q, yeah, it's logical to say that Q plus increases the Fermi number. So yeah, so we multiply the annihilation operator by the creation operator for the fermion, which is just the Grassmann number psi. And for Q minus, we use the annihilation operator for the fermion and the creation operator of the original problem. So we consider these two operators. Now we shall see why these definitions are interesting and make sense here. Now, the usual, what is supersymmetric quantum mechanics without the talk of all those potentials and superpotentials and their asymptotics and the degeneracy? What is the crux of the matter? The main idea is to have two operators of supersymmetry, that is Q plus and Q minus, and for them, together with the Hamiltonian, to form a graded Lie algebra. So let's move this a little bit further down, since it's not the right time. But what we have is Q plus, Q minus, and H. So Q plus and Q minus are odd. H is even. And the commutation and anti-commutation relations in the algebra look like this. So we want Q plus and Q minus to be symmetries of the Hamiltonian. And that means that they commute with H. Also, well, since q plus and q minus, their relation should be an anti-commuting one. So it should be an anti-commutator of q plus and q minus. And here, well, of course we could put 0. That would be a very simple algebra. So that's not very interesting. So that's why here we put the only other element that we have. It's the h. So that's the only structure that we can. That's the only interesting structure that we can get for a Hamiltonian with two supersymmetries. And it is, I guess it's easy to see that one supersymmetry wouldn't be enough. We wouldn't achieve much with just Q. All right. So this is the general structure. And now we can introduce Q plus and Q minus in the way that I already wrote before. And let's see what supersymmetric problem arises from such definitions. Let's anti-commute Q plus and Q minus and see what we get. Now, this is an anti-commutator of psi A, and A is dx plus w prime, and d psi minus dx plus w prime. Yeah, so, well, it's easy to see that in this anti-commutator there are two terms, and since the bosonic and fermionic parts are independent, we can multiply them independently. So the first term is just psi d psi. Let me leave A and A dagger here. We're not in a rush. Then let's write it here. We have two terms. The first term has a following fermionic part, and the bosonic part looks like a dagger. And the second part is d psi psi and a dagger a. Great. But let's see, a and a dagger and a dagger and a are precisely our partner Hamiltonians. So this is our H1, this is H2. And what do the fermionic parts mean? Well, they're just projectors on the space, on the subspaces. This is a projection, and this is a projection on the fermionic subspace. And this is a projection of on the bosonic subspace. So what are our spaces and subspaces that I'm talking about? Well, the space of functions that we consider in this problem are H. It is let's see how I should write it. It should be, I guess it should be C. Well, let's say L2 of R, and also with this Grassmann variable psi. So, and this has a very simple structure. Since psi is odd, this basically means that we have functions and psi times those integrable functions. Here that we use L2 as our space is not very important. The main idea is that our functions split into the bosonic and fermionic part. And what here the projection operator acts in the clear way. That's how the fermionic projection operator acts, and this is the bosonic operator. So we just get the bosonic or fermionic part of our function. Great. So this super Hamiltonian H is just the first Hamiltonian for bosons and the second or partner Hamiltonian for the fermions. That's great. That's exactly what we needed. We got a structure that incorporated both of the partner Hamiltonians. So yeah, let us see how Q plus and Q minus act here. And I guess then it should be time to make a break. Yeah. So what's the role of Q plus and Q minus? Well, by construction, they are symmetries of the Hamiltonian. That's easy to see. We're not gonna, I don't think we need to check it. Yeah. So let's see what it means in practical terms. All right. So the general eigenfunction of H. Well, that's some phi. How should we call it? I guess let's still call it phi n. Yeah, and we'll look at phi n as we'll split it into boson and fermion parts. Yeah. So let's see what the Q plus symmetry means. Q plus symmetry means that if this is an eigenstate of the Hamiltonian, the supersymmetric Hamiltonian, and the energy is En, then Q plus phi n is also an eigenstate of H and with the same energy. Let's see. Yeah, so that's H. Here we have yeah, let's rewrite. No, it's fine. So Q plus acting on phi n, it destroys this psi. This psi squared gives 0, and we're left with psi a acting on phi n boson. Now, if we write H as a let me move it a little bit. If we write H as we did before, as the H1 times the projection on bosons plus H2 and the projection on fermions, we see that only the projection on fermions survives, and we have nothing but H2, A, phi, and boson. But we've already seen the structure. That's how we started to look at the degeneracy of levels. And we can see that well, since this boson, in practical terms, it means this index 1 that we used before for the functions. So a little bit of confusion in notation. Please excuse this. We can see that that's by definition, practically, a phi n is an eigenfunction of H2. So we rewrite it as energy and a phi n bosonic. Well, that's what we needed. Have I missed something? Right, I missed up psi. Yeah, there should be a psi here. And psi a is q plus, clearly. So this is just en q plus phi n bosonic. Well, but that this pn bosonic can clearly be replaced by the full phi because q plus acts on the fermionic part as 0. So these are not some kind of deep computations. This is just to check that our picture is, well, it agrees with itself, with the previous iteration. With the language of partner Hamiltonians, that it is the same as this supersymmetric picture. All right, so it's 12 o'clock sharp here in St. Petersburg. So I guess let's make a 10-minute break as usual. And then continue and see what are the implications of this supersymmetry. Maybe anybody has questions? This is kind of, I guess, introductory stuff for supersymmetric quantum mechanics, but I don't know how about you, but we haven't studied this in the university, so nobody told us that such things exist. So that was kind of new for me.
Is it some standard thing to formulate this partner Hamiltonian in supersymmetric quantum mechanics, or is it?
Well, I'd say yes, especially if well, this language of partner Hamiltonians, as we shall see after the break, allows us to construct a whole hierarchy of Hamiltonians, a whole spectrum of them. Well, yeah, an array of Hamiltonians, and with very nice properties. They would be related in an intimate manner, and there. So this language of partner Hamiltonians allows us, to construct, as I said, this array of Hamiltonians, and as it turns out, to solve the original problem for the H1 or H2, it would be enough to find just the ground states of all the previous or following Hamiltonians in that hierarchy. So I'd say, yeah, it is. I'd say it's the standard way, and it is a very productive way of looking at all of that. But more about that after the break.
Okay, thank you.
So let me share the screen again. Right. So what I forgot to do was to draw the probably the most important picture, at least for visualization, to see it in your mind. And here's how it looks. So we have the first Hamiltonian H1, the Hamiltonian H2, and let us draw the state, their states. So for H1, we have a ground state phi naught with 0 energy. Well, let me guess. Oh, 1 second. Let me draw some kind of energy axis here. That would be 0. And here it would be phi naught. And for every other state of H1, phi n1, we have a corresponding state for H2 with the same energy. This is En1. And it is acquired by applying the annihilation operator A. And yeah, so this is A, phi, N1. And for every state of H2, let's call it phi M2 with energy EM2. We have a corresponding state in H1, which is acquired by applying a dagger. This is just phi M. A dagger applied to phi M2. What is important is that we have no well, so all these states are paired in a way. They're in these in these pairs, but we have no pair for phi naught. It is all alone because A just gives 0 here. We have no corresponding state for H1. Right. We have no corresponding state for H1, and we have no 0. So that means we have no 0 energy state for H2. If we had a 0 energy state for H2, that would actually mean that a dagger acting on this state is 0, and then applying well, 1 second, let me gather my thoughts. Well, yeah, it's very simple. Assume that we have a ground state for H2 with 0 energy. That means we have some phi tilde 0. This is 0. But if we look at what a dagger is, it's minus dx plus w prime phi naught tilde. And if we solve it for phi naught, we shall find that phi naught tilde is some constant times the exponential of, similarly to what we had before, in this formula, we had the exponential of minus w of x, but here we'll have the opposite sign since we're acting with a dagger and not a. So we'll have a w of x. And if w of x has the proper asymptotics for phi naught, original phi naught, to have to be a bound state, that means to tend to zero quite rapidly on both of the infinities, then phi naught tilde by definition cannot be a bound state. It will actually grow indefinitely in both the directions. Yeah, so if phi naught is the ground state of H1, then H2 has no zero energy ground state, and all its energies are actually above. So the structure is, they can erase, it's not a very important point. That means all the energies are above this zero, and they're all paired, of course. Okay, so this is how it looks. And in terms of supersymmetric problem, this is the bosonic part, and this is the fermion part. And we see that, yeah, that we have zero energy corresponding to this zero fermion number. All right. So the next thing is so we could go on and see how the let's so we have formulas that connect the states. That is, if we know a state of, say, H2, we automatically know a state of H1 and vice versa. And the formulas are pretty simple. We just apply A and A dagger. Well, but this was about bound states. But we know that above all of this, let's let me move this to the below. We know that above, starting from some energy, we might start to see unbound states. This does not occur in the most popular supersymmetric quantum mechanics problem, that is the supersymmetric quantum oscillator, because its potential does not allow for any unbound states. But our W prime, our potential, which is W prime squared minus or plus W double prime, might actually tend to some constant at infinity. Nobody, it could do that. We will see a few examples where it does that, and that means that we might have the continuous spectrum here. And what about this continuous spectrum? Do we have a similar story there? Well, as it turns out, we do. If here we have some state with energy E, let me denote it by phi E, and of course 1. Then let us see that acting by A on it, we'll get an unbound state with the same energy for H2. This is a straightforward calculation, and well, it's not really calculations. Very, very simple. We just see that phi E1 solves this equation. Let's call it E1. And then we just we rewrite H1 as A dagger A, and we act with A from the left. This is essentially the same thing that we did before. There's not much difference. The above calculations actually did not distinguish between bound and unbound states. Well, it was a matter of our notation, actually. So this is nothing else but H2 acting on A by 1. Yes. And this is just E1 A by E1. Yeah, so the unbound states are also related by these creation and annihilation operators. And that is very, very convenient. Why is it convenient? Because well, the topic of this seminar was like symmetries of amplitudes and applications in supersymmetry, examples from supersymmetry. And here we'll see the first example from supersymmetric quantum mechanics. We'll see how the amplitudes work here. So what do we call amplitudes in quantum mechanics? Well, the usual formulation is as follows. We have I think it's a just solution. I might be mispronouncing it, but let it be just the solution of say the first Hamiltonian with energy E. It has the following asymptotic. It is defined by that it is a solution and that it has the following asymptotic behavior. As x tends to minus infinity, it is just the wave approaching from the left. Before I write it, I guess I should be more precise about what our problem looks like. Since there are problems where there are no unbound states, let me draw a picture. So this is V. And for unbound states to exist, we'll consider V's that look something like this. That is, they tend to some constants on the left and on the right. So this should be V minus, and this is V plus. This is X. What does it mean for the superpotential? That means W prime squared. Here's how, now for the first Hamiltonian, it's minus, so it's minus W double prime. It should tend to V minus as it goes to minus infinity and to V plus. Well, the simplest case when it's satisfied is when W prime goes to the square of V minus, also constant. and to the square of v plus. Here the signs are unimportant, of course. The overall doesn't matter. Could be plus or minus. But that's a lie. These signs are important, but they're important for the bound states. Because if W prime tends to some constant, that means that W tends to X times some constant. So in the sign of that constant is responsible for the asymptotic behavior of W. And that defines if we have bound states or do not have bound states. Or rather, if we have the ground state in the form presented before. All right, but for unbound states, we shall not think about this. Fine. So W behaves like this, and we shall call this W minus and W plus. And this allows us to find at least the asymptotics of the unbound states. So let's consider an unbound state with some energy E, and I don't know, I'll draw it like here. It goes like a wave, then it I don't know, there's something happens to it, something is reflected, something is transmitted, and let's see how such solutions look like. So yeah, let us have a what is called a just function with energy E, the first Hamiltonian, and it solves H1 with energy E, E1. And its asymptotic behavior is as follows. We consider a scattering problem where we have a wave coming from minus infinity. And this wave is normalized. And by normalized, this might have an overall factor of 1 over the square root of 2 pi, but I will not worry about that because it doesn't matter in what follows. It's an overall factor. So here, E to the, so it's falling, so it should be with a positive momentum, and P squared is E1. No, not E1, sorry. It's not E1, it's E1 minus V minus, right? So I guess it should be properly denoted by P minus. So it's the impulse at minus infinity. Also, in this wave that is coming from minus infinity is reflected and transmitted. The reflected part is here. We'll call it R of, let's just call it R for now. It might depend, it will depend on the energy, but I'll not, the only thing let me call it E, and it's first. Yeah, and it's this is reflected, so it's going in the other direction, but the absolute value of the momentum is the same. At plus infinity, we have a different picture because it's similar, but the momentum is different because there the kinetic energy is different. It's E1 minus V plus. So here we have a outgoing wave, and it looks like this. This is again 1. Right. So, as we know, we have a symmetry, but not a symmetry. We automatically have an unbound state for the second second Hamiltonian, and that means that if we know RE1 and TE1, so that is the reflection and transmission coefficients in the first problem, that allows us to construct them in the second problem automatically. Let's see how it's done. Let's act with A1 by 1E. And this is just dx plus w prime acting on phi 1E. And obviously, we're interested only in the asymptotic behavior. So let's see how it goes. Well, when x tends to minus infinity, we know that w prime tends to w minus, and dx acts, well, only on the exponents, because that's the only dependence on x that survives at minus infinity. So if I just act on each term on the falling wave, the wave that comes from minus infinity, I will get I pi minus plus w minus times this wave. And I will also get plus minus I pi minus plus w minus or E1 e to the minus I pi minus x. And when x tends to plus infinity, I have a similar story, but w prime tends to w plus. Oh, I guess I should have denoted w prime minus. Yeah, here are the primes. Yeah, I guess this is the only place where the prime notation is really inconvenient, because we want w prime minus to be constant. So let me just write it here so that there shouldn't be any confusion. Sorry about that, but having a prime here saves us from writing an integral in the definition of the ground state. All right, so on plus infinity, we have a similar story, but w prime tends to w prime plus. So what we have is and the momentum is different. So we have just this times T E I plus x. All right. Now we notice that, well, this is obviously never 0. So this, just by rescaling by this factor in front of the falling wave part, we can get the just function for the second problem. This is just marvelous. So we write that this is just a by 1e rescaled by I pi minus plus w prime minus. And the asymptotics they are as follows. E minus infinity plus infinity. I pi minus x plus minus I pi minus plus W minus prime over I pi minus plus W minus prime. Those are E1, E minus I minus x. And here a similar factor, but the signs are a bit different. I pi minus plus W minus prime. E1. Yes, and here we immediately recognize that this is nothing but RE2, and this is TE2, the reflection and transmission coefficients for the second problem. Yeah, so this is great. Not only are all the functions related to each other by the application of A and A dagger, or we could think about it in supersymmetric terms by the application of Q plus and Q minus, but also the unbound states are related, and conditions are imposed on the transmission and reflection coefficients. Moreover, we see that the factors that appear here are actually, well, very simple. They're just phase factors. It is clear to see that the absolute value of each of one of them is 1. So these are just, so that reflection and transmission coefficients in the two problems differ only by some phases. So we can write it as e to the I, say, delta R, RE1, and e to the I delta T, TE1. What are the consequences? The consequences are, well, one of the consequences is that if we have what is called, one of the potentials is what is called reflectionless, where R is equal to 0, where nothing is reflected. And this happens, as it turns out, quite often in solvable problems. Then the second problem is automatically reflectionless as well. So reflectionless potentials are paired together. They're yeah, that's great. Yes, very simple structure. All right, so and these two numbers, R and T, which are actually, they're related by the familiar condition, which arises from the, well, you see, it arises from the conservation of probability current in quantum mechanics, which is equivalent to the the unitarity of the S matrix. So these are just, so this is the scattering data, the reflection and transmission coefficients. And in these supersymmetric problems and in partnered problems, they're related by a very simple relation. All right, are there any questions about the scattering part? All right, maybe there'll be some more questions later on. All right, so now we could either look at an example, or we could go on to shape invariant potentials and construct a hierarchy of Hamiltonians. So, well, I guess it would be in the spirit of these seminars to consider an example after all these very general words. So let's do that. Example. And let me consider an example that has both bound states and unbound states. Yeah, and with our present knowledge, the only thing we'll be able to find are the 3 bound states. Let me think. All right, we'll consider 2 very similar examples. So we'll consider a very particular form of the superpotential, that is w prime of x equal to some number L, which in these examples will be integer, but this allows some generalizations to non-integer L as well, but that will probably come later. So times the hypertangent of hyperbolic tangent of x. So that's how I'll write it, th for derivative. All right, so let's see what partner Hamiltonians such superpotential produces. Well, h1 is minus dx squared plus the square of the w prime, so it's L squared hypertangent squared minus d prime, the w double prime. So it's L, and the derivative of the hyperbolic tangent is 1 over hyperbolic cosine squared. I'll write it as ch again for derivative. And if we expand the hypertangent squared as 1 minus 1 over cosine squared, we arrive at this form plus L squared, a constant. That's interesting. We'll see what it means in a moment. And then minus L times L plus 1 over cosine squared. All right, for H2, we have a very similar situation, but there is a difference in signs here. And it produces, oh, sorry, we write H1 as an index here. So this is minus dx squared plus L squared, and then minus L times L minus 1. Collecting the terms, that's what we get. All right, so this is related to what we'll discuss probably next time. That is, here, the potentials in H1 and H2 turned out to be extremely similar. They turned out to be some constant over cosine squared, hyperbolic cosine squared. That is not the general case, unfortunately. If it had been, then all the potentials would be solvable, more or less, yeah. But this is kind of a special situation. But we'll not exploit this similarity to the fullest today. We'll just study examples of what we've covered in the previous 1.5 hours. So let's see. Let's fix L to be, to study the bound states, let's fix it as 2. Then our then our Hamiltonians are h1 is minus dx squared plus 4 minus 6 over, and h2 is minus dx squared plus 4 minus 2 over cosine squared. So we can draw the potentials on one level, because the overall shift in energy is the same. We see that h1 and h2 are similar. They look like a hole, a well, but they just have different depths. So h1 looks something like this. Well, the potential in h1, and the potential in h2 looks something like this. That's how 1 over cosine hyperbolic cosine squared looks. Fine. So let's see what our machinery tells us. We know that h1 is a dagger A, and h2 is a dagger. And we say that h1 a dagger A its ground state is found by solving a phi naught. Let's drop this one here. A phi naught equal to 0. Now this can be easily solved, since A is just dx, and the superpotential is 2 times the parabolic tangent, phi naught equal to 0. You can solve it in the usual way, or we can notice that such a W prime produces W that is L times the logarithm of the hyperbolic cosine. Let me think about the, yeah, and there should be no overall minus signs. Yeah, so, and we know a form for phi naught using this W. We instantly write phi naught of x as some constant times the exponential of minus W, and this is nothing but hyperbolic cosine to the power L. Yeah, very nice. In our case, L is equal to 2. So let me put this formula here as a general one, and we shall use it with the 2. Yeah, so that allows us to find a bound state for h1, for the ground state for h1, and it's somewhere here. Notice that the depth is 6, and the energy of this state is actually -4. We can see it because there's a +4 here, and we know that h1 acting on phi naught is 0. So the energy is -4. All right, so that's the ground state. Now, what about the other states? Well, so far, using the general formulas that we got, there's not much else we can say. We can say that had we a state here or here, we could find its partner in the other Hamiltonian. But the general theory does not tell us how to find those non-ground states. However, and this is what we'll cover in depth next time, we will already use this self-similarity. We actually we see that solving the problem for h2 is not any different. Yeah. So we see that we know that had we a 1 here, let's see how it looks. Dx plus hypertangent acting on some, let's call it, yeah, let's call it phi naught 1. And this should be, this we'll call phi naught 2. No, that's bad notation. This suggests as if it's a partner. Let's call it just some phi 2. Doesn't matter. We know that this produces equal to 0. This produces phi 2 equal to some constant, over cosine, just the power is not 2 but 1. And if we plug it into H2, we see that it is actually a solution. Well, and that is expected since H2 and H1 are very similar. They are just they differ only by this parameter L, and this L differs by 1. Again, we'll see in details how all of this works next time. But here it's enough to say that H2 is actually solved by phi 2, and the energy is, as it is not very hard to calculate, it's -1. Well, I will. I don't want to. Yeah, I don't think we should go into a calculation here because this is not the time to talk about it. Let's just say that we found this phi 2, which lives here. This phi 2. This is phi naught. And then that allows us to instantly construct the correspondent state in H1. And this is constructed by acting with a dagger. That's how we get from the second problem to the first. Let's just construct it. Let's call it phi 1, this state. And phi 1 is a dagger acting on phi 2. And this is minus dx plus 2 hypertangent x acting on phi 2, which is some constant over hypercosine. So, and if you compute it, the derivative gives hypertangent over hypercosine, and so both of the terms in a dagger give the same thing, and the result is just 3c2 hypertangent of x over hypercosine of x. This is just we should take a derivative. Nothing difficult here. All right, let's draw them. Let's draw these. And this is not, well, it's a very complicated function, but probably not something we could just guess for H1. All right, so let's draw them in this picture. Let's draw phi naught, which is basically a constant over cosine squared. Well, it's very similar to our potential, but inverse, right? Not inverse, but with a different sign. Phi 2 is similar, but the power is 1 less, so it's more. It's more wide, and phi 2 is 1 over cosine multiplied by the tangent, and the tangent function has a node, has a 0 at x equals to 0. So we get, as one should expect, a function with one node. Now, this is great. We now for H1, we have two functions. We have a ground state function without nodes, and we have a something which is actually the first level and actually the only level in this H1 problem. And it has one node and it is denoted by 1. All right, that's the bound. That's the bound spectrum. That's the bound states and the discrete spectrum. Actually, in this problem, it is exhausted by these energies and these functions. That's all there is to it. But we shall see it. We shall prove it next time. Let us see how the unbound states work. Well, here, if we just try to solve something like H1 phi equals to E more than 0 phi, we'll be kind of stuck. I don't have an idea how to solve it directly. At least nothing bright. So let us consider the case L equals 1, which is of fundamental importance here. The L equals 1 case is very similar, but we have for H1 we have what do we had H2 before, a hole of depth 2, and this is our H1. We'll move it. And for H2, if you plug L equals 1 here, you see that the potential actually vanishes. And H2 is just a free problem. Now, this is great because the free problem, this is something we can definitely solve. The free problem has no bound states, but we're not looking at bound states right now. We know all about them here. But let's look at a unbound state with energy E. For H2, it's just E to the I E of x, the px, with the momentum p squared equals to E. So this allows us to find the unbound state for H1 by acting with a dagger. Let's call it, I don't know. Maybe let's not. Let's act with a dagger on E to I x. And this is nothing but minus dx plus hypertangent of x. L is 1 now. So if we act, we see that it's just minus I phi plus hypertangent times the exponential. All right, so this is non-trivial. This plus tangent, this is something which is not easily guessed, as I think, from the trying to solve H1 phi equal to E phi, the Schrodinger equation for H1. But this is what we got automatically by this partner potential language, or supersymmetry equivalent here. So it will look, well, I don't know, I guess something like, doesn't matter. Great. What's more, we can find the scattering data for H1 right away. Let's look at the scattering data for H2. Well, it's not very interesting. The phi for the second problem, well, it's just it's just e to the IP x. So it's asymptotics. It's just it, nothing else. So that means that we have r equal to 0, r2, and we have t e to equal to 1. Well, that's expected. That's the free problem. But let's use our formulas that we got before here. Well, not them, actually, the kind of inverse of them. I studied going from problem 1 to problem 2, but we need to go the other way. That just means that we have to apply not A, but A dagger. But this is, let's see what changes. Not much. So A dagger applied to phi E2 is, well, we know what it is, right? It's minus I pi. We just calculated it. And the asymptotic behavior is as follows. When x tends to minus infinity, the hypertangent is -1. So we have minus I pi minus 1 times the exponent. And as it tends to plus infinity, we have minus I pi plus 1, because that's what the hypertension tends to. By rescaling, we get the asymptotic behavior of, and let me cancel a minus sign here for it to be more readable. And this is the asymptotic behavior of the just function of the first problem. And p squared is equal to e. And this is our non-trivial result. We got that for the first problem, r is still equal to 0, because the r in the second problem was equal to 0. So our potential, which is -2 over hyperbolic cosine squared, is reflectionless. Well, that's if you know it, you know it. But when I guess when someone first sees it, it's kind of surprising. But we also got something non-zero and non-trivial, which is the transmission coefficient, which turned out to be I pi minus 1 over I pi plus 1. Yeah, this is just a phase. And this phase, let me see if I can say right away what this is. I guess I'm not gonna. Not very important right now. So it's just a phase vector. All right. So it seems that our time is up, but I hope that well, the only thing perhaps I haven't demonstrated is how the supersymmetric structure here works. But I guess you can relate this picture with this picture in supersymmetric terms, and see that we have a single ground state, which is bosonic. This is phi naught. And for the supersymmetric, let's say in supersymmetric, we also have a phi equal to phi 1 plus psi phi 2. That would be the non-zero state. All right, yeah. So any questions? So briefly recall, we factorized the Hamiltonian.
I have a question.
Yes.
So in this last example, we get H2 equal to 0, right?
Well, the potential in H2 equal to 0.
Oh,
yeah.
Okay, yeah, okay.
Yeah. So, sorry, this should be a picture for V1 and V2.
V2. Okay, yeah.
H2 is
Because
just a free.
Yeah, all right. So
Yeah,
we didn't lose supersymmetry here. That's just the potential.
Yeah, we didn't lose it. What's interesting that this free problem is actually as when put as the fermionic part of our superpotential, where the boson part is this -2 over hyperbolic cosine. This exhibits supersymmetry. That's um, uh, so we have a free problem supersymmetric to something as a part of a supersymmetric problem. And as you see here, it allowed us to instantly solve for the just function, and well, E could be anything, so that allows us to find all the unbound states for H1. Yeah. Which without this connection would be rather challenging to do, I guess. All right, so this is how it looks like. Yeah, so what we did was factorize the Hamiltonian, and then we constructed a partner Hamiltonian, which was the same creation and annihilation operators in the different order. Yeah, we looked at what the asymptotics of W mean for the existence of the ground state. Right. We saw how the A and A dagger connect the other states, not the ground state, but all the other ones, including the unbound states. Then we turned to supersymmetry and formulated this problem, connected the two partner Hamiltonians into one. Yeah. This expression here for H, this one, of course, could be expanded in terms of W prime, W prime squared and W double prime, and this psi and deep psi. Like could write it, but it's not very illuminating, I guess. It looks just like those Hamiltonians, but for bosons it turns out to be H1, and for fermions H2. Right. Yeah. So we saw that the states are just the boson state or the first state plus psi times the fermion state or the second state. So this is the picture that one should have in mind when thinking about supersymmetric quantum mechanics. Then we talked about unbound states, reflection and transmission coefficients, and how this symmetry allows us to connect them between two problems. And we considered two examples. One, with the three bound states, one single ground state and two paired states. And then we considered a simpler problem and found the unbound states here, seeing that the first problem could be solved by solving the second problem, which turned out to be the free problem. All right. So.
Sorry, this V2, it's not zero, it's just constant, right?
Of course, this is drawn up to a constant. I'm sorry, I have to answer the I have to answer the door. I'll be back in 30 seconds. Oh, yeah. Hello. I'm back. Yes. You're right. V2 and V1 are shifted. As you can see here in H1 and H2, there's a shift L squared. And it is equal to 4 in the first first problem. So the zero of energy actually lies here. Oh, not here. Sorry, that's -6. That's the level of -6. So actually, it's here. So the energy of the ground state is actually 0. Yeah. And here, oh, so I guess here's where I did wrong. -1 after this shift becomes 3. Yeah. So the proper way. Let's draw it in red. The actual energy starts here at 0. Here it's equal to 3. And the unbound states begin with energy 4 or greater. Right. It's in this problem. And in this problem, it's similar. The again, I'm drawing, this is -2, but we need -1. Sorry. This is the 0 of energy. This level is 1. So the bound states begin with energy 1 and greater. So yeah. So when I wrote P here, I meant when I wrote P squared equals to E, that was before the shift. So, or should I say after the shift? So the actual relation is like this. Yeah, because the energy is shifted. Sorry about that. Here. Yeah, and this is the question of the overall shift. It will be important later on, because this idea that the ground state has energy 0 is what allowed us to so easily factorize the Hamiltonian. So if it were some constant, the equation would be a bit different, and maybe it would be well, to solve it we should first shift it anyway. That's the most convenient form. Yeah. All right.
Thank you.
Okay, so we are closing to the end of our session. So we will continue with examples next time on Tuesday. So hopefully we will discuss Coulomb example and this rectangular potential example. Okay.
Yeah, but actually there are quite quite a few interesting examples. But with scattering, yeah, we'll try. I guess we'll try the square well, the finite square well. Yeah, but so far, I guess we covered everything that we planned except for the hydrogen atom and the shape invariance and the hierarchy of Hamiltonians.
Okay, so we will continue. So now it's
Yeah.
now time is
Oh, I need to
is
close the door again. So yeah, I guess we should stop.